Much of the western half of North America comprises a northerly trending couplet of distinct yet intimately interrelated tectonic entities, the Cordillera and the Western Interior Basin. The mostly high-standing Cordillera consist of varied geological terrains, complexly mingled, mixed, rifted, and amalgamated, and mainly ranging in age from the Paleozoic to the present. Whereas to the east, the Cretaceous Western Interior Basin was generally a subdued, low-lying asymmetric drainage trough that received sediment from Cordilleran uplands to the west, as well as more muted Cretonic topography to the east. How the two regions relate to one another has fascinated geologists for over 100 years. Our goal is to describe a narrow time slice through the trough and to explore the linkages between it and rocks of the Cordillera. The stratigraphy of the trough has been divided into a number of cycles or inundations. Here we focus on a relatively narrow slice of time at 100 plus or minus 5 million years or so, as shown in red, between the older severe and the younger Laramide orogenies. In Canada, equivalent older rocks are known as the Manville group. This next slide, modified from the recent GSA bulletin paper by Singer et al., shows the critical 4039 argon and uranium-lead TIMS ages of ash beds that provide detailed resolution of events. Most ages are on the average plus or minus 30 to 50,000 years. Our interests today mainly lie above those rocks colored in pale yellow. These include the shoaling upward sequence of sandstone, conglomerate, siltstone, bentonite, and coal, colored gray, and comprising rocks of the Blackleaf, Taft, Muddy, and Newcastle, as well as many similar units in Canada, such as the Viking, Bow Island, and Peace River. These units are overlain by a few tens of meters of dark shale with intercalated bentonites colored green, a condensed anoxic and locally bentonite-rich succession known as the Mowry Shale fish scales formations colored pink, and a series of westerly derived clastic wedges shown in brown. Note the progressive eastward younging of the gray-colored units. Each succession, the Taft, Blackleaf, Muddy, and Newcastle in the United States, involves shoaling of offshore facies and deposition of sandstone followed by fluvial channel development and subsequent submergence and burial by marine muds. A typical section is shown here and is from Lecky of Canada, but it provides a representative section through most of the correlative units in both countries. Note that Walther's law indicates that this vertical section also represents lateral facies equivalents. Because the units are progressively younger eastward and involving a migrating zone of uplift and exhumation, followed by submergence below sea level, we interpret the units to represent material eroded and deposited on a migrating forebulge swell. But because the swell migrated over something like 600 or more kilometers, it is too broad to represent isostatic flexure related to thrust loading. Instead, we infer that it represents a migrating flexural bulge related to westward dipping subduction of the cretonic margin as it flexed downward into the trench. The temporal control on the Canadian units is not as robust as those in the western U.S., but sparse data suggests a similar scenario. If we are correct, then the North American cretonic lithosphere must have been rather stiff. Here are two models, each using different temperature assumptions for North America to calculate the effective elastic thickness of the North American lithosphere. On them I have labeled the cretonic hinge line and the more or less coincident thrust front. Because the Western Interior Basin sits almost entirely east of the North American cretonic hinge line, the effective elastic thickness of the North American craton, which is a measure of its flexural rigidity, was likely in excess of 100 kilometers, perhaps even 150 to 200 kilometers, according to Tesaro et al. This is because the thermal regime primarily controls the flexural rigidity, and except perhaps close to the hinge line, where there may have been some ductile necking during creation of the Cambrian margin, at 100 million years, there was likely thick cretonic lithosphere located there. Subsequent heating from extension and magmatism in the much younger Basin Range and Rio Grande Rift zones destroyed the original cratonic thicknesses present at 100 million years. With an elastic thickness of 125 kilometers, which would be entirely reasonable for an area of Precambrian cratonic lithosphere, Fleck et al. Calculated that the flexural wavelength would be nearly 1,100 to 1,200 kilometers and increased proportionally with a thicker elastic thickness. This is consistent with the distance from thrust belt to the Black Hills, which is about 600 kilometers or half the wavelength. Therefore, we favor flexural bending of the cratonic lithosphere as it entered the trench, augmented by isostatic subsidence along the margin caused by the bulk of the thrust stack and related post-collisional sediments sitting on the lithosphere. Returning to our timetable, we note a thin, dark shale, say 10 to 30 meters thick, with intermediate bentonite beds known mostly as the Shell Creek Shale, or in Canada as the Shaftesbury Westgate or Sully, depending on location. Note that the Shell Creek Shale is the same age as the more easterly Newcastle Formation. In all locations, the dark shales pass progressively upwards into a distinctive silver weathering marine unit dominated by siliceous volcanic debris, bentonites, and porcellanites, known in the United States as the Mowry Shale. It and correlatives extend the width and length of the basin, even occurring as the non-marine mustn't-touch-it member of the Cedar Mountain Formation in central Utah. The Mowry comprises very finely interbedded graded siltstone and mudstone deposited by storm-driven bottom currents and a more distal mudstone facies deposited by pelagic settling, all deposited in a restricted oxygen-starved environment. The unit is characterized by abundant fish scales, bones, and teeth. It is overlain by various members of the Frontier Formation. In their 1960 contribution, Reside and Cobbin mention a section just under 60 meters thick containing 55 bentonite beds. Several of the beds are known to extend for hundreds of kilometers. Singer et al. Obtained 4039 argon ages of about 98 and 97.5 for bentonites in the Mowry Shale, the Western Powder River Basin, while Hannon dated one bentonite within the Mowry Shale of the Black Hills by ICP-MS on zircon to be 98.3. Reside and Cobbin, also in 1960, recognized 5 ammonite zones in the Mowry Shale of Wyoming. They're all Neogastroplites species, and they were apparently endemic to the early Cenomanian of the Shell Creek Mowry Sea. Within the foothills of the Canadian Fold Thrust Belt, nearly 500 meters of alkaline volcanic rock sit on an interfinger with conglomerates of the Bruin Creek member of the Mill Creek Formation and are known as the Crow's Nest volcanics. Here's a thin section showing phenocrysts of analcime and black melanite garnet xenocrysts in a green matrix dominated by clinopyroxene. An average of 2 uranium-lead ages obtained by Dinupana from the xenocrystic garnets gave 102.9 plus or minus 1 million years, which is within error of a titanite age obtained by Larry Heeman from an alkaline sill located just to the west. During our study of Cretaceous plutonic rocks of the North American Cordillera, we found that by using certain trace elements, we could regularly distinguish between arc and post-collisional magmas, which we inferred occurred during and after slab breakoff. Here we show pre- and post-100 million year magmatic rocks from the Peninsular Ranges, batholith. But similar temporal and compositional variations occur over the length of the Cordillera. We plotted some of the less altered 101.5 to 95 million year bentonite samples collected in Wyoming and analyzed by Hannon. The rocks appear to be post-collisional, not arc magmas. The trace element composition of the Crow's Nest volcanics are shown by red triangles here and are similar to those of the previous bentonites shown in green. We also plotted for comparison data from late to post-kinematic alkaline plutons, such as the Lochboral and Isles and Loyal plutons of the Scandian orogeny within the Shadus Highlands. And one can see that they are compositionally similar and probably all deserving of much greater study. Here is a correlation diagram for the Canadian stratigraphy, mainly taken from Block, but with numerous additions. The Crow's Nest volcanics are shown in the west, and one can see the Walton Creek, Paddy, Viking, Bow Island, and Newcastle formations. These are the so-called migrating forebelge rocks we've seen earlier, spanning the basin from west to east and colored blue. Just as in the U.S., those rocks are overlain by a thin succession of dark shales, here called the Goodrich, Cruiser, Shaftesbury, and Westgate formations, depending on location. The shale units include what is known basin-wide as the fish scales marker, or formation, shown here in red. The fish scales unit is similar to the Mowry of the western U.S., with which it is always correlated, except that it apparently doesn't contain as many bentonite beds. It is readily traceable over the basin, contains abundant fish debris, and represents a condensed anoxic horizon. It forms an essentially isochronous surface throughout the basin, and during its deposition, the slope of the basin turned from gently west dipping to very gently eastward dipping. While the endemic Neogastroplites fauna are not found in drill core throughout the Alberta Basin, within exposures of the fish scale zone in the foothills, Neogastroplites localities are common, as shown here, and provide direct correlations with the Mowry. Lying directly on top of the fish scales horizons are northwesterly derived dark shales, sandstones, and conglomerates of the Dunvegan and Shaftesbury formations, which collectively form a westerly derived clastic wedge and deltaic complex. Bhattacharya divided the formations into 10 alemembers that coursen northwestward and sit directly atop the fish scales horizon. Plint took it even further and used over 5,000 gamma ray and resistivity well logs and over 80 outcrop sections to map the various alemembers of the wedge and show that individual prodeltaic cliniforms sit directly atop the fish scales horizons for over 800 kilometers, clearly documenting the starved and isochronous nature of the fish scales. But note that even here, the uppermost alemember A extends some 250 to 300 kilometers, documenting, along with the relatively thin overall succession, a very stiff cratonic lithosphere. Buchmann dated zircons from 5 samples of sandstone from the Viking and Dunvegan, which clearly show 2 source regions, the Canadian Shield to the east for the Viking and Cordillera to the west for the Dunvegan. I plotted one of Hadlari's samples from Cambrian rocks just west of Orogeny on the lowermost panel for comparison. I'm not sure if you can see it. Heading even further north, we next look at rocks exposed along the Hume River of the Peel Plateau at the north side of the Mackenzie Mountains. Note the abundance of 99 to 85 million year old post-thrusting plutons in bright red located in Selwyn Basin to the southwest. On the Peel Plateau, we find from the work of Schroeder, Adams, Hadlari, and others, the easterly derived Martin House sandstone in yellow, passing westwards and upwards into thick mudstone unit, the Arctic Red Formation. The mudstones were uplifted, exposed, and eroded as documented by a capping sequence of ferruginous paleosols. The paleosols are overlain by a thin succession of mudstones that lie beneath the fish scales horizons, which is included in the overlying Slater River Formation. Like our more southerly sections, the fish scale horizon and related shales are overlain by westerly derived clastic debris of the Trevor Formation, which contains deuteridal zircons younger than 100 million years, as you can see. Just like their Canadian counterparts, muddy sandstone and Mowry Shale are overlain by a westerly derived clastic wedge, known in the U.S. as the Frontier Formation. All of the units have 99 plus or minus 2 million year deuteridal zircon peaks, with those in the Muddy and Mowry likely derived from airfall, whereas those of the Frontier represent debris shed southeastward from the rising hinterland. A sample of the older graybill at the bottom shows a likely Appalachian source, probably reworked material from the Allegheny and Foredeep as shown. While the frontier and equivalents occur in the Wyoming salient northeast of Great Salt Lake, all along the western side of the Colorado Plateau there is abundant evidence for 100 million year sedimentation and exhumation. In Montana, Carapa documented the start of exhumation in basement massifs of the Beartooth and Madison ranges at 100 million years, as did Pujols and others farther south in the Charleston, Nebo, and Canyon Range Pavant regions. Still farther south, the Iron Springs thrust, as well as the muddy thrust and their associated debris, such as the baseline and Willow Tank formations, are dated to be about 100 million years. In the Spring Mountains and southward to the New York Mountains, Michael Wells and his students, as well as others, have documented abundant exhumation and sedimentation at about 100 to 98 million years. Heading into Mexico, we first note that the lithosphere may have been quite different. So in addition to it being warm enough for carbonate buildups to develop, the basin might have behaved somewhat differently. Nevertheless, we find west-facing carbonate ramps and platforms, shown here in blue, sitting on North American crust that were overthrust from the west at 100 million years by rocks of the Guerrero superterrane, then intruded by post-collisional plutons of the La Posta suite between 99 and 85 million years. This figure through the uppermost section of the west-facing Guerrero-Morelos carbonate platform shows the disconformity atop the west-facing platform overlain by deeper water carbonate turbidites and faunal-rich condensed zones, all overlain by shale and Mezcala flysch. Tim Lawton investigated Mezcala flysch in central Mexico. 2 detrital zircon samples of his display the typical less than 100 million year post-collisional signature. This sketch map of North America shows the approximate extent of the mid to late Sedimentarian Western Interior Basin and 5 major and coeval westerly derived clastic wedge deltaic systems. Remember that beneath the clastic wedges that the stratigraphy is more or less the same over the length of the basin, and so suggests a plate scale rather than local origins. This figure attempts to summarize the sedimentary development of the Western Interior Basin over a 100 million year time span during the Middle Cretaceous. Number 1, uplift, exposure, and stream incision as the craton rode up and over the migrating forebulge. 2, infilling of the incised channels by swamp and shallow marine sediments as the margin submerged under the starved outer trench. 3, deposition of thin successions of dark shales intercalated with bentonites. This period marks at least local slab breakoff and initiation of breakoff magmatism. Number 4, as convergence stopped and exhumation began in the hinterland, the basin became an anoxic dead pool with stagnant conditions and abundant airfall tuffs. By time number 5, clastic detritus from the west had flooded the fish scales horizon and transported detrital zircons and other igneous debris younger than 100 million years old across the basin. The simplest way to explain the mid-Cretaceous sedimentary succession in the basin is by westward subduction of the leading edge of North America. It seems impossible to create the eastward migration of the peripheral bulge over a distance of at least 600 kilometers by isostatic flexure related to loading by thrust sheets and or sediment. Also, the consistent broad width of the basin rule out any need for dynamic topography. The mid-Cretaceous age is consistent with ages of deformation and magmatism in the Peninsular Ranges origin to the west. The post-100 million year debris arriving from the west is readily explained as post-collisional plutonic detritus shed from the exhuming hinterland. This chart attempts to illustrate the continuous extent of the Peninsular Ranges origin from Alaska to Mexico. The arc on the Peninsular Ranges composite terrain was active from 130 to 100 million years when it collided with the western margin of North America above a westward dipping subduction zone. Following collision and slab breakoff, large quantities of post-100 million year debris were shed both eastward and westward from the rising hinterland belt. The mid-Cretaceous sedimentary and volcanic succession of the Western Interior Basin is a perfect eastward continuation of the origin and supports west-dipping subduction models at that time. We end by noting that not only did the collision add the Peninsular Ranges composite terrain to North America at about 100 million years, but it also brought Yes, immigrants. That's right. According to paleontologists, tyrannosaurs, pachycephalosaurs, marsupials, and snakes all arrived in North America during the mid-Cretaceous. We suggest that they arrived on the Peninsular Ranges composite terrain. Thank you very much.